Greetings, everybody. So I'd like to show you a little bit about this problem from our assignment, and it goes like this. I'm given a definite integral, and I have a graph to accompany it, okay? And when I solve this, if I was working the assignment, part of the point of it is to make this connection about the answer to this definite integral and the way that this graph appears to be. In order for me to tell you about that connection, I want to go about like this. I want to talk a little bit about the relationship between definite integrals and area. Okay, so I give you two scenarios to think about. All right, suppose I have this graph of some function f of x, and it's entirely above the x-axis from a to b on the x-axis. Also, suppose I know, or suppose the truth is that the area of that region in red, that region below the curve, above the x-axis, from A to B on the x-axis, suppose the physical size of that region is A, capital A. Capital A, some positive number. Just the area, how big that space is. Then the ultimate answer to this definite integral, the definite integral from a to b, f of x dx, however you get that answer, it has to be capital A. So the integral will tell you that area. All right. Now, that more or less is the connection between area and integrals, as long as I show you this one other case. Okay, so this time I have a function f of x, and it's entirely below the x-axis from a to b on the x-axis. And suppose again I say, well, okay, the area between the curve f of x and the x-axis here in red, okay, the physical size, the area of that region in red, suppose it's capital B, okay? Then in that case, the definite integral from a to b, f of x dx, is negative b. It's the opposite of the measured area of that region. Okay? So if I knew somehow, whether by direct measurement or whatever, that this area was b, and that would be a positive number as a measurement of the area, then the ultimate result of this definite integral would be the opposite of b. Okay? All right. Now, any other case we would see, say the curve weaved up and down on the x-axis, crossed over the x-axis, went negative, crossed back over, went positive, then what you would see for any definite integral is some mixture of positive and negative. All right. Now, that's what I think I see here, right? So my definite integral corresponds to this curve from negative pi over 4 to 7 pi over 4. And I see in this case that the curve is not entirely above the x-axis or entirely below the x-axis across that region. Okay? All right, that's fine. I could break it up into these cases, though. I could take negative pi over 4 to this point where it crosses over here, 3 pi over 4, and I could solve that integral. And then I could take the graph from 3 pi over 4 to 7 pi over 4, and I could take that one and I could add them together. We can do that with definite integrals. But if I did that, because this region, which you see faintly in green, I guess, that looks kind of like a green color to me, and this region, I don't know what color to call that, but maybe like a light orange or something, I don't know. They seem to be the same size. And so for that reason, I expect this definite integral, when I solve it, however I solve it, to be 0, okay? Because it's like they cancel out. It's kind of like saying that I measured this and it's A, and then I measured this other one and it's the opposite of that. And then if you add them together, I get nothing. I get 0, okay? So that's why I would expect the ultimate result of this definite integral to be 0. Okay, now I don't know how big that region is in green or how big this one is, but they seem to be the same. And it's for that reason that I think I'm going to get 0. So let's see how you do that. Now, how would I verify this? This is just what the answer seems to be. Just looking at the graph, because these regions appear to be of the exact same size. How would I know? Well, I can use the fundamental theorem of calculus to solve this definite integral and give you a definite final answer, okay? And so here's how I would use the fundamental theorem of calculus. So I find the antiderivative of this function. So the function sine x plus cosine x. The antiderivative of sine x is negative cosine, and the antiderivative of cosine is sine. Sure enough, you can verify if I take the derivative of this, I'll get sine plus cosine. In that antiderivative, I put 7 pi over 4 in first, which is the upper bound of the integral, and I subtract, and I put negative pi over 4 in second. I calculate each of these, and I get what you see here. And sure enough, they are the same number, but opposite of each other. Okay. And I get 0 all said and done. All right. Okay, so that's what I expected. And this is the math, the work that would prove that. All right. Okay, so I would put in, if I'm working this on my math lab right now, 0 would be the obvious answer for me. Okay. And then this last part is to make the connection, as I said, between the area and the integral. Okay. Now, so which choice of these seems to be what I was saying? It would be this first one. This answer, 0, is consistent with what I see in the figure because the area below the x-axis appears to be equal to the area above it. Yeah, so it's because those seem to be exactly the same that allows them to cancel out like this over here. If one was a little bigger than the other, then that wouldn't happen. But because they appear to be the same, then I know that that's the way that it's going to work out, as long as that appearance is actually the case.